All right, having you step a little outside of your comfort zone, I know you guys love trig functions, so here is a function that is defined as a trig function, 1/2 x minus sine x, on the closed interval 0 to 2 pi. One of the things that you should know about this particular problem is it would open itself up to asking about absolute maxes and mins due to the closed interval. So if I find the critical values, I could ask you questions about that. Again, in this particular case, I just want to show you the first and second derivative test and what it tells us about the function 1/2 x minus sine x on this given interval. So again, the first step is we're going to take the first derivative. So y prime is just going to be 1/2 minus cosine x. And I think we all know that 1/2 minus cosine x is just a transformation of the cosine graph. The cosine graph is defined at all values on its domain, so there are no undefined values for which I have to worry about this. So really my only concern is where is cosine x equal to 1/2? And since I'm only dealing with the domain 0 to 2 pi, I don't have to write the generic x value. I only need to find the values on 0 to 2 pi for which this is true. This is where the reference angle is pi over 3. So pi over 3 is clearly one of the answers. The other answer is going to be in the fourth quadrant with a pi over 3 reference angle, and that would be 5 pi over 3. So these are the two locations where the derivative is equal to 0, which can be found by setting cosine x equaling to 1/2, which means that my intervals are now broken into 0 to pi over 3, pi over 3 up to 5 pi over 3, and then 5 pi over 3 up to 2 pi. Now notice what I did here that was a little different than the last problem. I did include the endpoints of 0 and 2 pi. They are in the domain. However, I'm just going to warn you, you probably shouldn't use those as test values even though they're in the interval. I would still choose a value that's between 0 and pi over 3 that you're comfortable using. Now with trig functions, be smart. Choose values that are special angles for your test values. For instance, between 0 and pi over 3, a good test value would be pi over 4. Between pi over 3 and 5 pi over 3, I would always use something on an axis if I could use it. So in this case, pi over 2 would be a great choice. You could have used pi if you wanted to as well. Between 5 pi over 3 and 2 pi, there's really limited choices in this one. I'm going to go 7 pi over 4. I usually choose pi over 4 over pi over 3 or pi over 6 when I have a choice, just due to the fact that I sometimes don't like having to remember whether or not I'm dealing with halves or radical 3s over 2. Just go radical 2 over 2 when I have a choice. So to find f prime of my test values, I'm evaluating the first derivative at each of these values. So that's going to be 1/2 minus the cosine of pi over 4. And cosine of pi over 4 is just radical 2 over 2. Again, what is that value? I don't really know. It's 1 minus radical 2 over 2. Radical 2 is bigger than 1, so I know that it's going to be a negative number. I'm going to do 1/2 minus cosine of pi over 2. And again, cosine of pi over 2 is simply 0, so 1/2 minus 0 is 1/2. My concern is this is positive. And then for 7 pi over 4, 1/2, again, cosine 7 pi over 4 and cosine pi over 4 are the exact same thing. So radical 2 over 2, which is again negative. So what I see happening here is I have a decreasing function from 0 to pi over 3. At pi over 3 it switches to a increasing function and then a decreasing function again. What that tells me, again, when I go decreasing to increasing, if I look at that on any type of graph, if you go decreasing to increasing, you have got yourself a relative minimum. When I go increasing to decreasing, if I'm increasing to decreasing, then my horizontal tangent line is that of a relative maximum, and possibly an absolute. We'd have to check it out if that's what the question wanted us to do. In this case, that's not what we're going to do. So let me clear a little way here and write my intervals of increasing and decreasing. So my intervals of increasing is simply pi over 3 to 5 pi over 3. My intervals of decreasing are 0 to pi over 3, including the 0, union 5 pi over 3 to 2 pi, including the 2 pi. So there's the first derivative test applied. All right, on to the second derivative test. So our first derivative is 1/2 minus cosine x. Find y double prime. The derivative of 1/2 is 0, minus the derivative of cosine is negative sine. So we end up getting y double prime equaling sine x. Ooh, this is a nice easy one. Again, sine x is defined everywhere, so I don't have to worry about it. So the question is, where is sine x equal to 0? And again, the domain restriction that we were working with was 0 to 2 pi. So I only have to consider values between 0 and 2 pi. And we know that it is equal to 0 at 0, pi, and 2 pi. Now, two of those values are actually the endpoints of my interval, so the only new critical value I get is x equaling pi. So I need to worry myself only between 0 and pi and 2 pi. Okay, so those are the values that determine my intervals. Again, some easy test values. I'm going pi over 2 and 3 pi over 2. Could you have used pi over 4 or pi over 3? Sure you could. I think I just contradicted myself. I said I used pi over 4 in the last one. Used pi over 2 here because, again, kind of thinking back to plugging into the second derivative, sine of pi over 2 is really easy to work with. Sine of pi over 2 is just 1. Sine of 3 pi over 2 is just negative 1. So clearly this is positive and negative, which indicates concave up, concave down. Verifying that at pi I have an inflection point due to the sign change of the second derivative, or due to the fact that f of x goes from being concave up to concave down. So my interval of concave up is simply going to be the interval 0 to pi. My interval of concave down would be the interval pi to 2 pi. So again, kind of putting that together, putting together the intervals of concave up and concave down, the relative maxes and mins, we get a graph that looks like this. And what you'll see is each of these ticks is actually a pi over 2. So going from what is pi over 2 to pi, 3 pi over 2 to 2 pi. So we're really only looking at this portion of the graph right here. You will see decreasing, increasing, decreasing. You'll see concave up, switching to concave down, so only two intervals of concavity. The change occurring at pi, which is right about here, and you can kind of see that's where that concave up starts to switch directions and go the other way, where your smile becomes your frown. Speaking of smiles and frowns, you should probably go try to do some of those homework problems and put a smile on your face, or maybe a severe frown, I don't know. Thanks for watching. Good luck. I'll see you later.